This is about the single cylinder four-stroke engine, and the torque diagram is given in this case. So you are provided with the mean torque line, and then you are provided with this different areas here. So the area which is between A and B is 1.2. The area between B and C is 0.45. So if you read the description of the question, so it's saying that the torque diagram for a single cylinder engine is shown in the show below. The area above and below the mean torque line is in centimeter square. So these areas which are provided is in centimeter square. So all these are in centimeter square here. uh, okay, and what you are again provided is that the vertical scale is 1 centimeter equal to 100 Newton meter. So on this case, 1 centimeter is equal to 100 Newton meter, and in this direction here, 1 centimeter is equal to uh, 90 degrees, or you can say it is equal to 5 by 2 radians. So what you need to calculate, the part A is that you need to calculate the mean engine speed is 1500 rpm. So you are provided with the mean engine speed, which is omega. So what flywheel inertia is required to limit the speed fluctuation to plus minus 2%. So you need to find out the inertia of the flywheel, which should limit the speed fluctuation to plus minus 2% here. And in the part B, you are asked to calculate. So if we want to limit the hoop stress to 5 megapascal, what would be the suitable diameter of the flywheel if the density is this 7200 kilogram per meter cube, and what would be the cross section area of the rim? Okay, so in this case, it's good idea that first we will just collect all the given data. So what you are provided is that the areas are provided in centimeter square, and 1 centimeter is equal to 100 Newton meter, and similarly on the horizontal scale, 1 centimeter is equal to pi by 2 radians. So this is our y-axis, and this is our x-axis. So if we try our part 1 here, so what you are required is that the mean engine speed is 1500 rpm. So omega is provided is that it is 1500 rpm here. What flywheel inertia is required to limit the speed fluctuation to plus minus 2%? So speed fluctuation is given, which is plus minus 2%, and you are need to calculate I of the flywheel here. So normally I that we will use is for both crankshaft and flywheel, but because in this question there is no information given for the moment of inertia of the crankshaft, so we will just consider the I, and we will call this that this is the I for the flywheel. In some numerical example, if you are provided with the moment of inertia of the crankshaft, so obviously then you will need to use that values also. Okay, so if we concentrate on this part 1 initially, so we know the equation for this specific case is that delta E, which was equal to I omega square, and then it was omega 1 minus omega 2 divided by omega. So this is the main equation that we will use here to calculate I. So in this case, I of the flywheel, which is unknown, but we need to calculate delta E, which is the maximum energy fluctuation. So you will calculate delta E from this torque diagram, and obviously you are provided with this value here, omega 1 minus omega 2 divided by omega, which you can calculate from this value here. So as you, and again, you are also provided with the mean RPM, which is this omega here. So now what we mean by the speed fluctuation. So the speed fluctuation means that if you consider the crankshaft speed, so this is the mean value, which is omega. This is omega 1, which is the maximum value, and this is the omega 2, which is the the minimum value here. So in this specific case, you are given that the speed fluctuation is plus minus 2%. So this means that this is 2%, and this is again 2%. So this is a positive and this is negative. So this means that that you can allow plus minus 2%, so 2% in this direction and then 2% in this direction. So from these you can calculate this term here, omega 1 minus omega 2 divided by omega. So now if you assume that this is 1 here, so then this will become 1.02, and then this will become 0.98. Okay, so what does it mean that omega 1 divided by omega will become 1.02, and similarly omega 2 divided by omega will become 0.98. So then if you subtract omega 1 divided by omega minus omega 2 divided by omega equal to, so it will become 1.02 minus 0.98. So this will become 0.04. So this value will become 0.04 here, and this thing is then you can write is that omega 1 minus omega 2 divided by omega, so which become 0.04 in this case here. So this means that if you are provided with the speed fluctuation, you can calculate this term here, which is what we call is the fractional speed fluctuation. Two divided by omega, and we also know the value of omega. Now to calculate I, we also now need to calculate delta E here, which we can calculate from the torque diagram here. So now if you consider the value here is the energy here is E. So we can say that the energy, so you can say the energy level at A and E and G. So if we consider that because A and G are the same point, because the cycle will repeat, so the starting point of this cycle will coincides with the end point of this cycle here. So if you consider the energy at A is E, so then you can calculate the energies at B, C, D, E, A, and F. So then energy at B, So it will become energy at A, which is E, and then you will subtract 1.2 here because it's a negative energy. Now you want to calculate the energy at C here. So you will take the energy at B, which is 1 E minus 1.2, and then you will 8 plus 0.45. So this will become E minus 0.75. And similarly, energy at you will calculate at D now. So this will become energy at C, which is E minus 0.75, and minus this energy here, the negative energy, which is minus 1.8. So what you will get is that you will get E minus 2.55. And now you will need to calculate energy at E. So energy at E is again energy at D, which is E minus 2.55, and then you will add this energy, which is 3.45. So this will become E plus 0.9, and finally you will calculate energy at F, which will become E plus 0.9, and then minus 0.35, 1.35. So this will become E minus 0.45, and finally you can calculate the energy at G, so which will become E minus 45 and plus 0.45, so which will become E. And as you see here that we already have the energy at G is automatically E, and you can also here can have the same idea here. So now we want to calculate delta E. So delta E is the maximum energy fluctuation. And this maximum energy fluctuation is the maximum energy in this case. So the maximum energy here is the energy at E, which is E plus 0.9. So what you can say is that E plus 0.9, which is the maximum energy, and minus the minimum energy. So the minimum energy is at this location here, at location D, so which is E minus 2.55. So this is the maximum energy in this cycle, and this is the minimum energy. This is the minimum energy in the cycle. So if you subtract the minimum energy from the maximum energy, you will get the maximum energy fluctuation. So in this case, delta E, you can say this is delta E maximum. This will become 3.45 in this case, and the units here are in centimeters square, so this should be in centimeters square. Now the unit of the energy is not centimeter square, so you will need to transfer this centimeter square to the proper units, and therefore you will need to multiply with the okay, so you will need to multiply this with these units here. So 1 centimeter equal to 100 Newton meter, and 1 centimeter equal to 90 degrees here. So in this case, if you multiply with these units, so it will become 3.45, into 100, which is equal to 1 centimeter equal to 100 Newton meter, and then 1 centimeter equal to 90 degrees, which is pi by 2 radians. So if you convert energy to this, so then it will become 541.9 joules. So this is the energy that we will get from this specific case. Okay, so now if we take the equation, so delta E, which was equal to I omega square and omega 1 minus omega 2 divided by omega. So now in this equation, and this is obviously the maximum energy fluctuation. So the maximum energy fluctuation, now we know that it is 541.9, and this will be equal to I. So I is the moment of inertia of the flywheel, which we need to calculate, and then you have omega square. So we are given that it is 1500 rpm. So you need to convert the 1500 into radian per second. So rpm revolution per minute, so it will become 2 pi divided by 60. So you convert this into so this is conversion from degrees to rpm to radian per second. So this is the conversion here. And obviously we already know the value of the omega 1 minus omega 2 divided by omega, which is 0.04 here. So if you do the calculation from here, we will get I, which is equal to 0.549 kilogram meter square. So this means that if you want to control the speed to be within plus minus 2%, so at the engine speed, so we need a crank shaft and flywheel with the total inertia of this 0.549 kilogram meter square. Okay, so if you want to write it, so it will be a good idea, that is to control to control the speed to be within plus minus 2% at this engine speed. We need to crank and flywheel with a total inertia of 0.549 kilogram meter square. So again, this is important, that the main objective of this flywheel is to control the speed to be within this limit here. Okay, so now if we go back to the question, now we want to calculate the second part here. So the second part was, if we want to limit the hoop stress to be within 5 megapascal, what would be a suitable diameter of the flywheel if the density is 7200 kilogram per meter cube, and what would be the cross section area of the rim. So in this part, what you need to calculate is that so here now in this part B, we are provided with the density, which is rho 7200 kilogram per meter cube, So you are provided with the density, and obviously you know the value of the I which you have just calculated, which was 0.549 kilogram meter square. This is the unit of the I, which is moment of inertia. uh, and you are also given that the you want to limit the hoop stress to be 5 megapascal. So the hoop stress is 5 uh, mega newton per meter square. And you are also given the mean speed of the flywheel, which is 1500 rpm. Okay, so we know the equation in this case, and what would be the suitable diameter of the flywheel. So what you need to know here is the diameter of the flywheel here. So you need to calculate the diameter of the flywheel. Uh, for the flywheel, we know that the hoop stress, we derive this equation, is equal to density times omega square into r square. Okay, now the another important thing here is that this omega is given, which is 1500 rpm here, but the we will need to design the flywheel for the higher speed, so it will be automatically safer for the lower speed, because the this is the mean speed, which is not the maximum speed of the flywheel. So the flywheel will go up to the maximum speed, which is omega 1. So in this equation we will always use omega 1, not omega. So again, this is very very important concept here, that you will design your flywheel to be safe at a maximum speed, not at the mean speed. So this omega will always be the maximum speed of the flywheel. So in this case, if you now put the values here, so from here you can calculate the R of the flywheel, and from the R then you can calculate the diameter. So sigma h is given, which is 5 megapascal, so you will multiply it with 10 power 6. On the right hand side you have a density, which is 7200, and you have omega 1, which is 1500, and then you will multiply this with 1.02. So this means that it is 2% higher than the mean speed, because what we were given is that the engine can go up to a speed of plus minus 2. So this is the speed fluctuation. So if you want to calculate omega 1, you will just multiply this 1500 by 1.02, and obviously you will need to convert this into the radian per second. So you will multiply this with 2 pi, and then you will divide this by 60. So this is in radian per second into and obviously this is square and r square. So from here you can calculate the value of the r, which is about 0.164 meter, or you can say it is 16.4 centimeter. And you can calculate the diameter, which is 2 times the radius, so which will become 32.9 centimeter. Okay, and another thing that you need to calculate, which was again part of this question B, part B, is if you go to the question here. Okay, so we managed to calculate the density, a suitable diameter of the flywheel if the density is this. And the second part is you need to calculate is what would be the cross section area of the rim. So the second part is that you need to calculate the cross section area of the rim of the flywheel. So if we go back to here, so the second part is that we need to calculate the cross section area of the flywheel rim. So as we know that if you consider this sort of thin ring here, and if this distance is r, so the moment of inertia for this specific case is always equal to I m r squared. And m is again the mass, and r is the radius here. So in this case here, because we are given uh, I, so we already know I here, and we know m, we know r, so we can calculate m here. So m will become equal to I divided by r square, so which will become 0.549 divided by 0.164 whole square. So this will become 20.4 kilogram. So the mass in this case will become 20.4. And now for the rim of the flywheel, we know that the mass in this case is equal to density times the volume. So the volume is equal to the circumference times the cross-section area. So this is the cross-section area in this case here. Or if you take it like this, so this is the cross-section area in this case. So this is the A in this case. So if you want to calculate the volume of this ring here, so if you take the radius here, the mean radius, and you multiply the cross section area with this circumference, so you will get the the volume of this this section here. So in this case, the circumference is 2 pi r, and then you will multiply with the A, which is the cross section area here. So in this case, now you are given everything. The only thing which is unknown is this A. So A will become equal to m divided by rho into 2 pi r. So if you put the values of the mass, which is 20.4, the density here is 7200, 2 pi, and into r, which is again 0.164. So this will provide you with the cross-section area of the rim of the flywheel, so which is 2.74 into 10 raised to power minus 3 meter square.